Alright, today we're going to talk about oxidation states. Oxidation states are one of the most commonly misunderstood concepts in general chemistry, and I think they really give the course the reputation it has for lots of memorization of nonsensical facts. I will be presenting the material in a very non-traditional manner over the course of 2 videos. In video 1, we will cover basics that will get you through the majority of situations. In part 2, I will cover more complicated situations, but in order to understand them, you need to have covered Lewis dot structures and bonding, which you might not have in your class yet. Now, there are numerous ways that the rules have been covered, but they all have the following things in common. Lots of memorization, there's some mention of a hierarchy, most students don't know what they're memorizing, and a lot of the grief is unnecessary. We just have to understand some simple concepts. To teach these concepts, I will start with some key definitions we must understand and then apply them to various situations. The first thing we need to understand are the concepts of bonding and electronegativity, which you may or may not have heard of at this point, depending on the structure of your curriculum. First, let's define a bond as 2 electrons shared equally or unequally between atoms. Typically, each atom provides 1 electron. There are some exceptions in the more complicated molecules that I'll cover in video 2. We will define electronegativity as the degree that an atom hogs an electron in a bond. The significance being that when atoms are bonded, electrons are either basically taken from one atom by another. This is what's known as an ionic bond, and this occurs when one atom just has such a higher electronegativity or ability to hog electrons than the atom it's bonded to. In other situations, the 2 atoms might have equal ability to hog the electron, in other words, equal electronegativity values, in which case they evenly share their electrons in what's known as a covalent bond. But in some cases, one atom definitely hogs the electron more than the other, but not so much that it fully steals the electron, in which case we call this uneven sharing, and we have a polar covalent bond. And so here is an example of an electronegativity table, where the value indicates the extent that an atom can hog an electron in a bond. Now, there are numerous electronegativity tables out there with different values, but what they all have in common is the following trend. Electronegativity increases up and to the right along the periodic table. Now let's move on to the main event, which is the definition of the oxidation state or oxidation number. They mean the same thing. The oxidation state is the charge an atom would have if the electrons in the bond were fully taken by the more electronegative atom. Let's see what I mean by this through example. We will quickly define an overarching rule that you already know, that the sum of the oxidation states must equal the total charge of the overall species. And the reason you already know this rule is because you learned it during nomenclature, as you'll see. Our first examples will be based on compounds that only involve nonmetals. It's for these types of compounds that oxidation states are particularly important to understand. And yet, because of the supposed hierarchy of rules that I'm largely ignoring because it's confusing and unnecessary, because of that hierarchy, these types of compounds generally get covered last. But we'll do them first because this really allows us to understand what oxidation states are. You see, when nonmetals get together, they share their electrons in the bonds because their electronegativity differences aren't that large. But we do know that sharing of these electrons is not always equal. And so let's see how that relates to this oxidation state concept. Let's say that I wanted to contrast H2O and F2O, and I want to figure out the oxidation states of every atom in each molecule. H2O looks like this, as you may or may not have already learned, and F2O looks very similar. Now, there are these things known as lone pairs, which you may or may not have learned about at this point. I don't need to draw those for these general basic situations. Although for the more complicated situations in part 2, I will need to take those into account. Now, just to make sure we're all on the same page, these lines represent bonds, and these bonds consist of 2 electrons, one from the oxygen, one from the fluorine, or in this case, one from the hydrogen. And these electrons are shared unequally according to our electronegativity table, where we can see that oxygen is more electronegative than hydrogen, but it's less electronegative than fluorine. And so I'm going to draw an arrow in the direction of the more electronegative atom to indicate that it pulls on these electrons more than the other atom. Notice I'm putting these little crosses here. This is like the technical way to draw these arrows in chemistry. And now it's time to apply the definition of our oxidation state. If we were to pretend that oxygen didn't just hog the electrons in this bond, it completely took them both for itself, what would the charge on each atom be? Well, in this make-believe situation, hydrogen would be losing its electron, and so we would say its charge would be +1. Same for the other hydrogen. And since oxygen is taking an electron from each hydrogen, it's gaining a total of 2 extra electrons, and we would say its charge is -2. Again, this is not what's really happening. There's just an uneven sharing between these two. We are simply pretending like there's no sharing whatsoever and oxygen's taking all the electrons. It's an easy way to keep track of which atom the electrons tend to be hanging around with. Now let's contrast this with F2O. The fluorine is more electronegative, so we're going to pretend like it completely takes that electron from oxygen, in which case it's like it's getting an extra electron, and we would say that each fluorine has a -1 charge. The oxygen itself has lost 2 electrons total between the two bonds, and so we're pretending like it has a +2 charge. Quickly take note of 2 things. First off, the oxidation states in both molecules add up to 0, which agrees with the overall neutral charge of each molecule. Second, I never referred to this table where usually we'd say something like oxygen has a -2 state unless there's a fluorine, in which case fluorine gets priority since it's higher on the table with a -1, and by this other rule oxygen is forced to be +2, which is like solving a Rubik's Cube with no idea what the motions are actually doing. Now I'm going to erase these and do another one. This time let's do CO2, which looks like this. Carbon is double bonded to each oxygen. In other words, there is a total of 4 electrons being shared, 2 from each atom. We see from the table that oxygen is more electronegative than carbon. And so we quickly apply our oxidation state logic to this. We're going to pretend like oxygen is taking both of the electrons that carbon has contributed to this double bond, and same thing over here. In which case, we would be pretending like oxygen is gaining 2 electrons, and on the other hand, carbon is losing a total of 4 electrons, which would give it, in principle, a +4 charge, or a +4 oxidation state. Again, all the states add to 0. Now let me do one more example. What if our atoms were identical? Like what if I had F2, where F is just bonded to another F? Well, since they're the same atom, they have the same electronegativity value. They each are able to hog the electrons in the bond equally, and we can't pretend like one takes the electron from the other. Instead, we just pretend like each one keeps their own electron. So I'll say equal pull, assume oxidation number is 0 since neither takes or loses an extra electron. And so the oxidation state is always 0 when the atoms in the bond are identical. Now, what if our compound involves a metal and a nonmetal, what we call an ionic compound, where the electronegativity difference is generally at least greater or equal to 2.0? Well, these are simple. We've already stated that the definition of the oxidation state is just the charge if the more electronegative atom took the electron entirely. That's basically what already happens with metals and nonmetals with their large electronegativity difference. So the rule in this case is that the oxidation number is just the same as the charge that each atom actually already has, and you know how to do this from nomenclature. For example, imagine we had lithium chloride. You should already know at this point that the charges on each atom are positive and negative. And guess what? Those are the oxidation states as well. There's nothing new to learn. This agrees with the oxidation state definition, because from the electronegativity table, we see that chlorine is way more electronegative than lithium. So we pretend like chlorine is hogging that electron 100%, which it already almost is, given that that electronegativity difference is so large. Having large electronegativity differences will almost always be the case when metals are paired with nonmetals. I'll do one other example in which I pair sodium and hydrogen. We typically associate hydrogen with +1 charges, but let's apply our oxidation state definition. Hydrogen is more electronegative than sodium. Therefore, we pretend like hydrogen has a full -1 charge and completely takes sodium's electron. Notice that I didn't need to memorize some rule like hydrogen is usually +1, but the exception is when it's part of a metal hydride, making it -1. We just investigate their electronegativity differences and apply the oxidation state definition. Done. Now, last and most certainly least interesting is the oxidation state for a single species by itself. For example, lithium's oxidation state versus lithium plus ions oxidation state. Well, in each case, we don't see these species being bonded with any different atoms, and so the concept of sharing and electronegativity becomes irrelevant. And the oxidation state really is literally just the charge that the atom would have. The rest of the definition regarding bonding is pointless. The oxidation state of lithium, neutral, is 0. The oxidation state of lithium plus ion is +1. If I had something like sulfur by itself, that would have an oxidation state of 0. S2- ion, oxidation state of -2. Very uninteresting. In a nutshell, when the single species is by itself, the oxidation number is just literally equal to the charge. Now again, there are more complicated situations that can arise, and I'll show some examples in video 2. But everything I covered here gets you through most of the situations you can encounter, and we don't need a deep knowledge or understanding of bonding and structure.